Okay. Okay, so come to the, I think this is the last class. Everybody has completed everything. We have more or less completed everything that we needed to do, so which is a good thing. So in the last class, we were looking at queuing theory, right? And the methodology that we are going to look at is the let's say one infinity model, right? So this is the notation that we are looking at. This first M here represents this is our arrival rate. And our arrival rate is normally denoted by lambda. This second M here is our service rate or service time. And this is denoted by mu. And we make an assumption here that the arrival rate is Poisson and the service rate is exponential, right? This one here is the number of servers. So in this case, since I have one, I only have one server. This first infinity here is the queue length. Yeah. Right. Any amount of people could be joining the queue. Now, so that simply means this: the population that's coming in, it's infinite, right? Lambda over mu. Yeah. Right. So lambda over mu need not be less than 1. But in most cases, what happens is that lambda over mu is less than 1 because the time that you take to service somebody will be greater than the time that they take to come in. So the rho that lambda over mu would be less than 1. Right? So that ratio. So you have a queue length or queue size. So the queue size is infinity. That means that there's no restriction on the size of the queue, right? People could just be coming in, right, over and over again. And this last one across here, this infinity here is the population that they're talking about. So the population could either be fixed or it could be infinite, right? Depending on the problem that you're looking at. So if we look at a simple example, right? If we look at a simple example like this, let's say, okay, put this a little smaller. If I have the examples that we used the last day, we could have like one server here, right? So this is one server. And everybody just join the line, right? So people just coming in, and there's no restriction on the length of the queue. So that means because there is no restriction, I could go to infinity. But sometimes there might be a restriction on the length of the queue. So sometimes you'll come to a server, but you might be waiting in a room or something like that, but the room only has space for 4 people, right? So you automatically put a restriction on the length of the queue. So over here, it might only have only 4 persons. But here we could take infinite length, or people could be joining in. Now, before we go on, okay, so everybody is clear with this notation, right? So there's as you read stochastic processes, you'll see queues, you'll see this area called queuing theory, and then you'll see another area that we call birth and death processes. It's the same thing, right? It's the same thing. So it's just the notation is a little bit different. So I'm just going to say there is a one-to-one correspondence between queues, or the types of queues that we have, and birth and death processes. Exactly. So anytime somebody is born, that is an arrival, and anytime somebody dies, that's a service. Well, that's not the kind of service we like, but yeah, it is it is a service, right? And I'll just write down the notation for the corresponding birth and death process that you will see in a question. That is a one-to-one with the MM1 queue. Huh? Anything that I say in class is a hint. But that is true. Seriously. It's not meant to be, no, it's true. If I say do this, do it. Right? So and yes, I will clarify your hints and things like that later on at the end of the class, right? Because I will give you an opportunity to ask me anything about the exam. Yeah. So this is our bootcamp process, the MM1 queue that we had before. This is what it looks like in the boot and that process, right? It looks like this. That x of t, where t is greater than 0, be a boot and that process. With birth rate lambda and death rate mu. Again, we use the same thing. We assume that lambda over mu, we call that rho, and we assume that this thing here is less than 1. And if PNT, so this is a notation that we have in both and net processes. So this is just a probability that at time t, you have n items, right? Or n persons existing. So PNT, and what you could find PN, which is the steady state distribution. Now, I just want to be clear that when we're talking about both and their processes, Anytime you see a birth, it's a Poisson distribution. So it's assumed. So let me just put this in red here. So the assumptions here is that the birth process is Poisson, right? With rate lambda, and the death process is the same exponential mu that we were talking about, right? So everything remains the same. So whatever you do for the MM1Q, the results would be the same for a simple birth and death process. So a simple birth and death process that will look like what we have is this. We'll have n items here and n minus 1 here and say n plus 1 here. So I could move from n to n plus 1 if there's a birth, and I could move from n to n plus 1 here if there's another birth. I'm supposed to say n minus 1 to n, the first one, right? That's a birth, and then if you move from n to n plus 1, that's another birth. But then you could move from n plus 1 to n with rate mu, and you could move back to mu. So this is a kind of dynamic thing, right? Where you have births coming in and deaths coming in, right? Now, one of the reasons why we have something called a steady state distribution is this. If you want to get any expectation on things like that, you need some table, right? You need some table with some probabilities. So you need Pn and you need n. So 0, 1, 2, 3, 4, etc. P0, P1, P2, P3, P4. So in order to find any expectation and any of those things that we mentioned the last day, like LQ and things like that, the expected length of the queue, we need some sort of distribution, right, for the number of people. And in order to do that, the first step is to always to get that that distribution that we call the steady state distribution Pn, right, which basically gives us a listing of the probabilities and the corresponding values for n. All right. So what I'm saying is that if you see something like this anywhere, right, in the future or wherever, this is equivalent to MM1Q, the results. All the results would be the same. Exactly. Yeah. Right. But the terms will be the same, meaning that when I say the terms would be the same, it will be a little bit different. So things like LS, LQ, WS, and WQ will still exist. And the formula that we'll be using will be the same formulas that we would have learned in MM1, right? So the Q, in this case, the length of the Q would be like the length of the population or the population size at a particular time, right? Before they have died, and the number of people in the system would be the person experiencing death or being serviced, as well as the persons alive, right? So there's a one-to-one correspondence between these things. Right, so keep that in mind. So if you see queues and things that are playing a part in these things here, when you're talking about a queue, you know, it's the number of people that are alive, right? And there'll be one person in the system, and in the system, it'll be one person being experiencing death, and all the other would be alive. Okay, so now let's look at some other, let's look at another Q queuing model that we have a MM1 N infinity, right? So again, this one here, the Poisson rate, the arrival rate is lambda. This one here is that the arrival rate is lambda. The number of servers, service time, so service rate is mu. The number of servers here is 1. But in this case here, the queue length is fixed at 10. Queue length, sorry, is fixed at n. So that means you are not so there are some queues like that, right? They only allow, so once you have like 4 people in the line, if a 5th person comes, they'll tell the 5th person go away, or the 5th person has to leave. There's no way he could join, right? And infinity is the population distribution, right? Okay, so these are my so this is my notation for this model. So here the queue length is finite. And when the system I should say when a person comes in, when a person comes in and there are capital N persons in the system, that person has to leave. Right? So these are the same probabilities that we are accustomed with now. So the first question is this. So the first question, what are the probabilities? Well, the probabilities would be P0, P1, P2, all the way up to what? P1. N, right? Because we could only have N persons, capital N persons in the system. So in the previous one, the MM1, the queue length was infinite. So we went from P0, P1 all the way up to infinity, but this time we are stopping at Pn. Mm-hmm.
That's like how
Mm-hmm.
anything like that.
It have PGFs. Yeah, you you could use PGFs, to generate these probabilities. So in this case, the sum of the PIs from I is equal to 1 to capital N. This is equal to 1, right? Because those probabilities here, they form a distribution. We could write that down as P0 plus P0 times rho plus P0 times what? Rho squared plus P0 times rho to the N, right? And this is equal to 1, right? So this is the formula that we used the last time in order to generate these probabilities, that P0 was the initial probability, then P1 was P0 times rho, P2 was P0 times rho squared, etc. Right? So this is another way we could sum these things. Well, what do we have in common here? We have P0, right? So I could just write take off P0 like that, right? And you could sum these, right? And we have this formula n plus 1 over 1 minus rho, right? So the sum of those rows from 1 to row n, it's given by that formula there. And this here is equal to 1. So the first thing that we need to do is we just make P0 the subject of the formula, right? So in this case, P0 it will be 1 minus rho over 1 minus rho to the n plus 1. So this is what P0 is. Well, okay, so let me not say anything. So P0 is 1 minus rho over 1 minus rho to the n plus 1. Right. If anybody wants something to drink or something like that, you let me know, right? Just have water in the kitchen. Just in case you're choking on. If we have this is the math seminar room. Yeah. Yeah. So n person in the system means anytime I use the word system, it means I'm including the person at the at the server, right? All right, so let's try to get properties that we were familiar with. LS, right? Anybody can remember what LS is? The expected what? No. If I put LQ, it will be that. So LS is the expected length of the what? System, right? So this LS is the expected length of the system. So LS is equal to the sum. Now, how many people could be in the system? You could have, and it could be 0 or 1 or 2 or 3 up to what? Capital N, right? So that means for this one, yeah, of course, for this one. So we have this formula here. So this could be written like, so this is n times what? Rho to the n times P0, right? Like that. The terms that does not have n in it, I could take outside, right? So I could take out that P0, and I could also take out a rho, right? So I could take out a P0, I could take out a rho, and this would be the sum of n into rho to the n minus 1, right? So n is 0 to capital N. Sorry. Right, so this is P0 times rho, and this is sum n is 0 to n, and this is the differential upper d rho of what? Of rho to the power of n, right? So this, now I could switch these things around. So I could put the differential on the outside and I could put the sum on the inside, right, like this. So now what I'll do is this. I will take this first, right? And this will be this part will be d rho. And the sum here would be 1 minus rho to the n plus 1 over 1 minus rho. And this is equal to P0 times rho. Right? Okay, well, to differentiate this, we could differentiate this using the what? Using the quotient rule, right? So just using the quotient rule on that, and let's see what we'll get. So I'll get P0 rho into the numerator is what? V by the differential of the top there. That's what? N plus 1. That minus? Yeah, minus n plus 1 by rho to the n minus 1 minus rho to the n plus 1 times the differential of the numerator. So that'll be 1, right? It'll be negative 1. So that'll be a plus, right? Right, so keep me on the straight and narrow, right, with this. So this is a 1 minus rho squared. Okay, so let's try to simplify the top a little bit. Well, first of all, let's take the denominator on the outside as well. So we get P0 times rho over 1 minus rho squared. And the numerator will look something like this. Let's see, 1 minus rho to the n plus 1 minus n plus 1 by 1 minus rho by rho to the n. So I guess all we have to do is just try to simplify this stepwise, so and see what that square bracket will reduce to. It will come down to this: 1 plus n times rho to the n plus 1 minus n plus 1 rho to the n. Right, so it'll come down to this. Okay, so this here could we could simplify this again, maybe. Let's see what we could have. LS is equal to rho over 1 minus rho into 1 minus rho to the n plus 1 Which middle term?
Not one right above here, and plus one.
If we expand it, what will happen at the top? We'll get 1, we'll get a minus what? N plus 1 to the row. Then we'll get a minus, and then we'll get a plus, because this minus here will dictate what happens here and here. All right. Okay, so we have well, I wouldn't say we have a little problem, but all we need to do now is in these problems, anytime they ask you to get a steady state distribution, so anytime you need the steady state distribution, you need to get rid of P0. So what you will end up with is that you will end up with a function in it that has P0 in it, right? Well, what you'll need to do is you'll need to replace this P0 with what we got before. That's all, right? So let me erase this. So I'm just going to substitute P0 equal to, now what will we get P0 as? It was equal to 1 minus rho over 1 minus rho to the n plus 1. Right? So this was P0. This is what we got before. And all I'm going to do is I'm going to substitute this P0 here with I'm going to put in that there. Right? So everything now will be in terms of rho. Right? So now we'll be able to work out everything. Right? Everybody okay with everything so far? Good. So let me just, so this is, so at the end, so I'm just jumping down to the end here, and I'm saying that LS is equal to rho over 1 minus rho by 1 minus rho to the n plus 1 into 1 plus n times rho to the n plus 1 minus n plus 1 multiplied by rho to the n.
So the point wasn't there, so
Yeah, it was finite, right? Yeah, it was up to capital N, right? So we were able to solve for P0 in terms of rho, and then so now this expectation here, LS, is only given in terms of rho and N. So now we could work out LS easily, right? By substituting values inside. Everybody okay with this? If anything is not clear, let me know, right? So this part here is n plus 1. This is n plus 1, and this is n, right? It's n plus 1 here too. Well, the best way to see what is taking place in these questions, most of the times, is to just take a numeric example and see, what is actually taking place. So let's take an example. So we are assuming that we have M1 with N. So we are fixing the size of the Q to be capital N, right? So we must have a arrival rate. Let's say this is 8 per hour. We must have a service rate. Let's say the service rate is 9 per hour. And let's say the number of people in the system is 10. That capital N is equal to 10. So that means that once you see 10 persons in the system, you can't join the system, right? You must leave. So let's work some of these probabilities and see. So the first one that we could work out is what is the probability that nobody's in the system, right? So the first one, what is the probability that no one is in the system? Well, if no one is in the system, that means this is just P0 that we have to work out, right? And we know that P0 is 1 minus rho over 1 minus rho to the n plus 1. So, of course, we know that rho is equal to lambda over mu, right? So this is what we are using down here. And when we substitute this, we get 1 minus 8 over 9 over 1 minus 8 over 9 raised to the power of what? N is 10, so that's 11, right? Okay. So this is about 0.15, around that, 0.1529. So that means that the probability that no one is in the line or no one is in the system is equal to 0.15. So that means that there's a probability that as soon as I arrive, I go straight up to the server, right? So this is the probability here. All right, so the next thing is this. What is P1? So P1 is rho times P0. And so this is 8 over 9 multiplied by P0, which is 0.15, right? That we got just now. So this is about what? This is how much? 0.13, right? 0.13. All right. So what's the probability that you have no Q? If somebody asks, okay, what's the probability that you have no Q here? Well, probability that you have no queue means that you could have one person at the server, right? Or you could have nobody at all. So the probability of having no queue is just a probability that of P0, well, it's just P0 plus P1, right? So this is what, 0.28, right? So this. All right, so what's third one? Was a problem? What? Mhm. Yeah. Yeah, so I don't expect you to memorize the formula, right? So that means that if I have a worded question or something like that, then it will have this step, like the first one, do this. So find a steady state first. And if once you know P, and then you'll be able to answer these, right? So what's the probability that there are 10 persons in the system? Well, this is rho to the 10 times what? P0, right? So this is the, and this here, this works out to be 0.04, right? 47, I think, yeah. So now I could ask the other question now. This is now in this example, capital N is equal to 10, right? So what does that mean? That simply means that we have a system where we have one server here, right? We have one person here, and we have 9 other persons in the system. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the total amount in the system is 10, right? Capital N is equal to 10. So one person here is being served, and you have 9 others, right? So when you ask the question, what's the probability that 10 person is in the system? This is the probability, yes. But now we could ask the question, what's the probability that a person does not join the system, right? If a person does not join the system, that means that when a person comes, the place is full. That means you have 10 persons. So it'll be just 1 minus that amount, right? Everybody get that? So if, okay, so, okay, everybody understand this probability here, right? The probability of 10 persons in the system, right? The probability of 10 persons in the system is just rho to the 10 by P0, right? That works out to 0.047. Now, that is a probability that you have what? 10 persons in the system. Now, if somebody comes from outside, what's the probability that that person can, let me see, person does not join the system? Yes, 1 minus that amount. No, the probability that existing that there are 10 person system is that. So what's the probability of 11 persons in the system? Zero. Right. So if there's a new person coming in, that means you must have 10 persons in the system. The probability that a person, okay, what is the probability that a person does not join the system? Yeah, it, what?
If it's like given that have things no one probability I will join. It is a given.
Yeah, if it's condition that we have 10.
By probability that some join at all. Okay. Now my question here. What is the probability? So is there any other condition? Like
No.
in general?
No, there's no condition. Once you have 10 persons in the system, the system is full. The person must leave.
So that will also be probable. It's probable that the common system full. But that is just you can that's just
That's just the system alone.
Yeah, somebody
Coming in. Yeah, okay, think about it like this, right? So think about it as 2 pieces. The pieces that you have 10 persons, or the piece that you have more than 10 persons. So this probability here is 0.047. But the probability for this part here be 1 minus that.
That is what that's impossible because it was a maximum Q resistance. So for sure, they can
So we can, but that is like, I think that is also considering if you have like 11 people and 12 students, right? Or if you have 12 people and 15 students, right? All of this is not possible.
So, okay, can you just state the problem question in that one more? That's the probability that somebody.
What's the probability that a person does not join the system?
So that's the same as the probability that the system is already full.
And that somebody arrives.
No, but you assuming that they're already kind of drunk. Because somebody kind of not drunk either, right?
Oh, okay, I see, okay, I guess that's.
I can see what you're saying, but mhm.
This kind of incomplete because it's not just 10 and greater than 10, it's 10, 9, 8, 7, 6, 5. So all of you make up the rest of numbers to give you a total of 1 to the probability of greater than 10. Because the probability of 10 alone is that, right? But then you also have the probability of 9, and the probability of 8. And then all of those sum together will give you 1. The
Mhm.
probability of 8 greater than 10 should be 0.
It should be 0. But I understand what you're saying. But I want you to just keep this in mind as well, that it could be construed that the probability that the new person does not get to join could be considered as 1 minus the P10.
So, oh, because 1 minus P10 would mean that they are.
The rest, yeah. But I understand what you're saying.
So, but if that the probability that they can join, the probability that they are less than 10, because what we have there will be P1, P0 plus P1 plus P2 plus P3.
Yeah.
The original condition.
Yeah, I understand what you're saying. So the probability distribution is this P0, P1, up to P what? 10. The sum of these probabilities should be 1, right? So that's the thing. So the probability, so what we're saying is that we have 10 persons here. And if a new person wants to join, what's the probability? Well, the probability of their joining should be 0, right? The person cannot join because they will leave.
Yeah, so that's given that they're 10,
Given that you have 10 persons in the system,
or without a condition.
without a condition, it will be 1 minus. But I could see what you're saying. I'll take a look at this again. But if there's a new person in the system coming in, and you have 10 persons, that's a probability there. So you're asking what's the probability that a new person, and I could see why you're saying that this is a probability.
So the only reason, the only
Yeah.
thing that can prevent the person from joining is that they are already 10.
Yeah,
So the probability that they cannot join should be the probability that they are 10. Not that the probability that they are less than 10. Because what you have there is that, because so remember, all of them sum up to 1. So
right.
1 minus P10 is P0 plus P1 plus 1 over P10. And all of those probabilities are will be the event that the person can join.
Yeah.
Which is not the above there.
That conditional distribution. If you already factor in that they can't join after.
Because there is no condition, so it's just an icon, but the only thing that is not joining is that.
Oh no, what's the probability that a person does not join the system? Does not join the system means there's 1 minus of the probability that it has 10 persons in the system.
It will be 10 and less, like 10, 9, 8, 7, because they get showing.
Right. So if the probability that you have 10 persons in the system, what's the probability that somebody, okay, I did not say anything. What's the probability that a person does not join the system? Does not join the system.
So that's the probability that this system is full.
Yeah.
And they are technically in the system.
To bring in.
Well, I'm a little bit difficult, you know, the idea. Depends on equivalent.
How many balls can consume when it doesn't get stuck?
no.
Could just speak like they want to be like.
They can like fuse the switch line, like.
No, but this is not, yeah, but this is not a feeling and things like that. And so the question is this, right? So the question is, what is the probability that a person does not join the system? The probability that a person does not join the system is 1 minus that we have 10 persons in the system.
So it would be 1 minus that they could join,
Right, and they
which
should
is,
join it.
which is 1 minus. Of P0 plus P1 plus P2
Well, it's a nine.
of the P.
No, I think I understand this well. I think it's that it does not join the system, and when you say can join, choose not to, and you can join and choose not to if there are 9 or 8 people, so it's almost probabilities is 1 minus.
See, that's it. Is that?
I didn't say anything. No, listen. I didn't say anything about that there must be 10 persons in the system.
Yeah, but so,
Yeah.
only so can the person come and decide not to come?
Huh?
Can the person come?
You make it, you're bringing feelings and all kinds of things.
So I
Okay.
really think it's.
Yeah, but I understand what you're saying, and that's just like conditioning on the fact that you have 10 persons in the thing.
So no, because what is, okay, if I come to the system and I do not join, what is the reason for not joining?
System is full.
So well then.
So then it means I equivalent that the system is full and I do not join. So the probability that the system is full is the probability that there are 10 people. So the probability equivalent
I wanted to think about it, that it could be construed that it is 1 minus P10. Right, so, okay, we'll have your 2 ways, but so this is one of the possibilities that we can have. So the probability that a new person, so what's the probability that a person does not join the line, does not join the system? That means that is 1 minus the probability that there are 10 persons in the system.
Well, I say, I don't know. All right. So perhaps at any given time.
Yeah, no, because the next person could be the 11th person.
You know, but so.
I know you I calculate it all.
That makes sense to me, when you go and you're like, how 9 people here, but it's not long. You leave.
Or like random, like on a Tuesday, we have 5 people and just Friday, just come and just happen to be 10 of that. It's not possible to every time all the other days. Okay, just particular days, but not every day will be good. Yeah, so what guys are you coming from, so or nothing?
I'm not saying anything about conditional and things like that.
Yes, so we don't condition it.
Yeah.
Okay. So 1 minus the 10.
Yeah.
Okay, so 1, you can look at 1 as being the sum of.
I know what you're thinking, I know what you're thinking. The sum of from 0 to
Yes, so what
9.
if you look at it at 1 minus 10, that's the probability that they are less than 10.
It is.
Which means I can join.
Okay, so if I say, if I work out any individual probability like P2, right? What's that?
Probability that they are.
Right. So what's 1 minus P2? Anything else could happen, right?
Yes.
All right, so the problem here is when you reach to the end of the line. When you reach to the end of the probabilities, you see all those in the middle, you could maneuver things like that. But when you reach down to the end where it's full, right? So what's the probability that, okay, that somebody could join the line? It means that 1 minus the probability that it's full.
Yeah, which is that?
That is the opposite of.
That is the opposite of what you
No, I'm saying it's 1 minus that.
No, what, so the probability that they cannot join, they cannot join is 1 minus probability that they can. Or the probability that's like
P10 is a probability that you have 10 persons in the system.
yeah, but isn't it full then?
Right. What is the probability that somebody could does not join the system?
Is it probability that the system is full?
So you say probability that somebody can't do it is 1 minus the probability that have any.
Yeah.
Could you explain that a little more? This is our or situation where is the higher.
No, it's just 1 minus P10. You could think of it as just 1 minus P10.
No, it's not all, like, you just.
The into
So I kind of wrap my mind around because he can the probability that the system is full.
Mhm.
And if the system is full, I cannot join it. And if I cannot join, that means it can only hit.
So what is the probability that a person does not join the system?
It's 10.
Maybe you could just explain a little more why it would be 1 minus. Maybe like that.
P10 is when it's full. I agree with you. But this is the question: what is the probability that a person does not join the system?
Okay, so what is the reason for
It's 1 minus P10.
We go why today.
The 1 minus the probability that the system is full.
So that's a
No,
probability
but
that the system is not full, which means I can join. That's a contradiction to it.
I could see what you're saying, but you could could also be construed as 1 minus, just a simple 1 minus that. I think the conditioning part, you condition on an equal to, and I understand that.
Because there's only one way to join it. Only one way, only one thing that comes.
It's when you
equal
cross
to
10. Yeah. When n is equal to 10. Yeah.
So the events are the same. And their probabilities should be the same.
So what's the probability that person joins?
1 minus P10.
Yeah.
The probability that the system is not.
Wait, no, in that case, you have to count the monkey cells and all of that.
But
No,
other ones,
no, it's not 0 because that would be I think that would be conditional.
maximum number.
Okay, so I will take a look at it.
So we're trying to say so.
And yeah, go ahead.
All right, so we're trying to say that the probability from 1 to 10, not full enough to 1, so it's still has space with.
But it sounds like.
Yeah, that's all I'm saying.
From 0 to 10.
Yes. Yeah, that's all I'm saying.
I understand what you're saying.
Okay, so
No,
From 0 to 10,
yeah.
everything will come up to 1.
Mhm. Yeah.
Can be up to 1 if you have a point.
I could understand how you, yeah.
For yourself. Able to do that.
Yeah.
All
I understand what you're saying. I will check it, but I believe it's just 1 minus P10.
So, okay, so let me ask you a question.
Mhm.
Do you agree that two events are equivalent? One, that the person does not join the system, and two, that the system is full, or in other words, the system has-
Yeah.
The equivalent.
No, I understand what you're saying. You know. I understand what you're saying. The probabilities are equivalent. Yeah, I understand what you're saying.
But it's saying that if you could, you explain how somebody could interpret it as being 1 minus 10.
It's just one. It's just a complement of 10. If somebody does not join the system.
But the complement of 10 would mean that.
Yeah, 0 to 9.
Can you then put in a way that says, okay, the system is full at P10, right? But you cannot join before, you cannot join after P10 is equating that matters with 1 minus P10. Because if you say it like that, then I can't understand. Because if P10 is a probability of there are 10 people there, right? You can come and not join. And then you can come after, but there are 10 people there and still not join. So I get that as being 1 minus P10.
So we can bring feelings into it.
Oh. Okay.
Okay, so I will check this one again and get back to you on this.
They have a chat there.
Oh yes. Does or does not get to join.
Yeah, exactly.
Don't know. P10, yeah, she's saying it's P10. Okay, so let's go on. I will check that. Okay, so the next thing is that from this we have to work out some other things like LS, and LS is equal to well, we need to get the effective rate lambda, which we call lambda E. And this is just lambda multiplied by 0.9529, right? So the effective rate is lambda, which is the rate, which is 8, multiplied by the probability that the system is not full. So that means you have from 0 to 9. So this works out to 3.856. Right, so lambda is equal to 8, and the probability that the system is not full.
So that is 1 minus.
Yeah, this is 1 minus 10.
And because that's the miles for numbers. Right. 0 times 1 number is
0.9529. Yeah, the effective rate in this case here, the arrival rate is lambda, but the rate at which the surface is being carried out, because we have n of these, we have to weight lambda. 7 point what? Yes, 7.623, right? 3, right?
how much people that actually
Be service.
that you'll have to pay people.
Yeah. Well, just one less than the full rate.
Okay.
Yeah, it's because it's P10, we use n equal to 10, so just one less than that. Yeah. So that's how we weight it. LS is equal to 3.856. This is what we have before. The length or the expected size of the system is 3.8. The waiting time in the system is given by this, is LS over the effective rate, which is 3.856 over 7.623. So this is 0.5. So you might be, so anytime you're setting up a queuing model and you want to get the optimal rate and things like that, the waiting times might, in some queues, might take less time. But you have to remember that while it's taking less time, okay, for customers to get served, there's a cost involved. Because the cost involved you might have to have a lot more servers and so on. And you have to hire people. So there's a pro and a con here. So the waiting time in the system here, when you have a fixed length of the queue, n equal to 10 is 0.5. But in the previous example, when we were dealing with the MM1, the waiting time was about 1 hour, right? So, okay, so this sounds good, but this there's a cost involved. Nothing is free. So the person who is setting up the queue or who's providing the service will have to do something. You'll have to limit the size of the queue, right? That means people are being turned away. That means that you are losing customers. So there is a ripple effect that is taking place. And the waiting time in the queue is the waiting time in the system minus the mean service time, which is 23.68. Before, in the MM1, it was 53 minutes. Now it's 23 minutes. So, okay, everything looks good. You spend less time waiting and things like that. But I mean, there's always a cost involved, and the cost is not as straightforward, you know, what you might think it is. Yeah, those are the other two, right? Right. So what I want to do now is have C servers now.
So steady state, what's the definition of steady state?
So steady state is analogous to what we did when we did a stationary distribution. Like pi is equal to pi times P, capital B, in a continuous time setup. Yeah.
Like infinite how we
Yes. Yeah, so it doesn't depend on any of the PIGs over a long period of time what will take place. And once you get a steady state, you'll be able to work out anything. Now there's this one now called the MMC infinity. So the first M again is the arrival rate, and we normally set it at lambda. The second M here is the service time, which is we say is exponential with rate mu. But now the number of servers is C, right? And again, the queue has infinite length or size, and the population, this other infinity, is not fixed, right? And so this is the MMC infinity. Anytime you see these Q questions and you don't see these last two terms here, infinity, it means that it's assuming infinity, right? So if you see MMC by itself, it means it's infinity. So now we have a problem now where we have arrival rate, service time, but now we have C servers, right? So it's something like this. So suppose we have 3 servers, and this is we have one line like this, right? Okay, so who can tell me what is the effective service rate now for something like that when you have C servers? C times mu, exactly. So we have C times mu is the service rate in this case. And we will assume that lambda over C times mu is less than 1, right? Or rho C is less than 1. This is service rate because the effective service rate only works when you are working out LS and WS and things like that, those things. But this one here is just looking at the queue here because you have C servers, then the rate is C times mu, right? It is not just mu because all of them, they are working independently of each other. So it's not like if you must do service here, then here, then here. So it's like in the banking system we have in Trinidad, normally one big long line, and you have tellers in front. And you could, as one teller is free, one person goes and yeah. So this is the MMC one that we have in the banking system. So lambda n is equal to lambda, right? Now n is the size or the number of people in the line. And mu n. Now this is a little bit different. It has 2 forms. It has the form n times mu if n is less than c. And then it has this form c times mu if n is greater than or equal to c. So the first one, if the number of persons that you have is less than the number of servers, then everybody's at a server. Right? So let's take this first one here. So if you have 4 servers like this, right? And you only have 3 people, then you have nobody in the line. So everybody is being served. What is the effective service rate in a case like that? It'll be 3 times the number of thing, right? So this is why you have n times mu. N is less than c. Yeah. Well, not the effect. In this case, the service rate will change depending if n is greater than c or less than or equal to c and things like that. It will change. So this is why mu n is broken up, but the arrival rate remains the same. So that's why I have here lambda n is equal to lambda. It doesn't change. That one is fixed. But now if you have the number of people to be greater than or equal to the number of servers, that means you have a line, right? So that means that all the servers now are being used, are being utilized. So the service rate in that case is C times mu, right? So that's why this is C times mu. Everybody get that?
And this is a rate, not time.
Yeah, this is the rate, right? Okay.
What's the mean is a rate?
A rate. Yeah. So we normally call it a rate. Remember how we define the MM1? We said the exponential with rate lambda or parameter. Yeah. Okay, so now we have Pn is equal to rho to the n times P0. So this is our initial conditions here, right? Which is equal to what? Ordinarily, you'll have rho being lambda over mu to the n times P0, right? So this is how we construe rho to be in the past, right? This is what we would think about in the past. But now we have a little bit, we have a little difference here, right? Because rho now, there's a breakdown here. So we'll have when n is less than c, we'll use this here as our mu n. And then when n is greater than or equal to c, we're going to use c mu, right? So it's going to be two pieces then we'll be looking at. Right, so let's take for n less than c first. In this case, Pn would be equal to lambda over mu times lambda over 2 mu times lambda over n mu times P0. Which is lambda over mu to the power of n. Anybody could identify. Okay, so this is n times, right? So this is 1, 2, 3. This is going up to n. So this is lambda to the n on top. We have mu going n times again, right? By what? Yeah, 1 over n factorial, right? Yeah, 1 over n factorial multiplied by P0, right? So this is the first one. And you think you could write down this one for me? N greater than or equal to c and see what it will be. So this one here, anybody could think about the formula for Pn now, this for n greater than or equal to c.
Lambda over C.
You're close, but lambda over what?
C times mu equal to 4.
Yeah, but there's a little issue there because of the n greater than or equal to c. And you have to factor in that. So the first one is lambda over mu. The second one is lambda over 2 mu. And the last one is lambda over c mu times P0, right? So looking at it like that, it seems as though that this here is a very simple thing. It seems as though it's lambda to the n over mu to the n times c factorial times P0. This is what it looks like.
I see that.
It looks like that, but it's not quite that because n is greater than or equal to c. right? So there's a little trick here that, we have that the highest part here that we have here is C, right? And N is greater than or equal to C. So anybody could. Okay, so I guess, well, we could see the C factorial, right? So we could see the C factorial. We could see the mu to the N, right? And this part here may not be quite obvious like that, but we'll have a C to the N minus C. This part here is because N is greater than or equal to C. You need to factor in this part.
So that means after you do like the same as it was for, but
Mhm.
after you reach C.
Yeah.
You continue multiplying by C that line.
Yeah, yep. Yeah, so C is C to the power of N minus 1. N minus C. All right, so let's work out these probabilities.
So,
Mhm.
you can just explain how yeah, yes, it's an less than all of this is not just like, well, using rho 3 and like E0. That they don't just say, well, rho is lambda over n mu, and then put that to the column and then
Rho is equal to what?
Rho is lambda plus if rho is lambda over c, that's correct.
And we're using this, yeah?
Yes.
Right.
So it have multiple expressions for rho.
Multiple expert. In this case here, rho is, remember, rho is lambda over C mu.
The rho to the power of n.
Yeah.
In this case, N is less than C, So it'll be lambda over mu by lambda over 2 mu going down the road until lambda to the N mu. So C wouldn't come into it at all.
That's why each of those is like a different rho or something or
No, remember it was fixed on the previous one.
right.
And this one is not going to be fixed, right? It's going to vary.
I'm trying to figure out how that translates multiplying each other.
What do you for multiplying? What is it? So the rho is what?
The rho to the N is rho over mu.
Lambda.
Yeah, lambda over mu. And in this case is lambda over C mu. Right? But this is a breakdown here. So you have two. In this case here, if you watch here, you have two separate mu n's. When n is less than C, this is what you're using. So your rho that you're using here would be lambda over n mu in one case, and the other one would be lambda over C mu. So it's going to be different.
So then, why don't just say, well, the n is rho 3 and like so lambda over n mu to the n.
And you have to look at n is less than C.
So the lambda over n mu is your rho for n less than C, right?
Yeah.
So then yes. lambda over n.
Raised to the power of n?
Yeah.
No, it can be. It's going to be different for each one, right? Because n could vary, right? But listen, you're making a general statement here, Pn. So P1 could be something. Then how you move from P1 to P2? You add an next row, right? Yes, but in this case, the other row that you're adding is not identical to the one before. So it's going to be different across the board.
So what would be lambda over 2 mu?
Lambda squared over 2 mu squared times P0. It's not going to be the same. Initially, initially we had the same row. It was just lambda over mu.
Right.
Once you change one of those things underneath and you put a number like C that could vary and things like that, then everything is going to change. It's not going to be the same. Like putting lambda over n times mu raised to the power n. Yeah.
Okay, I guess I understand. I don't understand how it translates in the product of lambda over mu.
Each one of the quote unquote rows would be different, right? So this one, yeah. So the first one,
The second one,
lambda over, yeah, lambda over 2 mu, etc.
So this one. Can I say?
P2 would be lambda over mu by lambda over 2 mu times P0.
So is it like, okay,
We just have a general statement, you know, we just put in Pn here, where n could be anything. So if n goes smaller, then we could cut off the excess to the smaller parts.
okay, so when n is less than C, that means you have less people in the system.
Yes, you have more.
So let's say the first person comes in, they go to one server. All the other servers.
No, when you say n less than C, that means you're taking everybody on one go, right? So everybody is in front of a server. Yeah.
Okay, so
Yeah.
Oh,
then
okay.
service rate depends on the number of servers that are occupied.
They what?
The number of servers.
Yeah,
that are
yeah,
occupied,
yeah.
Which one use the n? The n is different for each.
That's why we have to split it up n less than C and n greater than C, because it'll be different. Yeah. Once the number of people in the system is greater than the number of servers, you have everybody being used up, all the servers being used up. But if you don't have that, then you have less people being used up, right? Okay, so this is our PN. Right, so this one, to get the steady state probabilities, so we know that the sum of these P0s, P1, P0, P2, plus, this should be equal to 1. All right, so this one is a little bit different from all that we have had before. So this is from, so I'll just write it down, n is equal to C0 to C minus 1, rho to the n, P0 over n factorial plus sum, n is equal to C to infinity, rho to the n over C factorial C to the n minus C times P0. So this is equal to 1. And you make P0 the subject of the formula. Right, so I'm not going to do that. So I'm just, yeah. Right, so the first one is where n is less than, and the other one C, and the other one is where n is greater than or equal to C. Right, so yeah, so this part here is Pn, where n is less than C. And this fancy thing here is Pn, where n is greater than or equal to C. So in these problems, the first thing is this: you have to get rho n, right? And all those probabilities you is equal to 1, then you get P0 as the subject of the formula. If you get P0 as the subject of the formula, you'll be able to get the first probability, independent of any constants, right? So then we could work out all the other probabilities that we want. So I'm leaving out some steps here, and I'm just saying that P0 is 1 over the sum of n is equal to 0 to C minus 1 times rho to the n over n factorial plus rho C over C factorial times 1 over 1 minus rho over C. So this part here just goes with this alone. So that next part here is the second summation that we had up there. Right, so this is so if this is P0, what we have now is this. We could break it. So our Pn now will be in two pieces, right? And this is what you're going to replace P0 with in the Pn, right? So for the two pieces. So you'll have for n less than C, you'll have Pn is equal to lambda over mu to the n times 1 over n factorial multiplied by 1 over P0. But this P0 here is this thing up here, this entire thing here, right? Multiplied by P0, sorry, not divided. Right. So that entire 1 over those, that sum plus that constant there is equal to P0. Yeah. So now Pn for n less than C is independent of P0 because P0 is given in terms of rho C and n, right? So you don't have any, so P0 is known, in other words. So we know the first probability, what P0 is. From that now you could build and you could get the other probability.
Okay, so just to confirm this
Mhm.
time, rho in this case, just to be sure.
For n less than C, rho was, we took it as lambda over C mu, right? Yeah. It was lambda over n mu. Lambda over n mu for n less than C. and it's lambda over C mu for n greater than or equal to C. Right, so it's this here. Yeah.
Like, I think it's literally a default that. But like, yeah, root, right?
Yeah.
Whereas it's actually like a product of lambda over and mu I. Think about that. Where I goes from 1 to n. So like when we take rho n, we take it as the lambda 1 over n by mu or whatever.
Yeah.
That you will go for like one particular value and I know what it and it's 10 times whatever, and then you put that in power of n when it's not that.
It's not that. No.
Right. So
Yeah.
I think that should be.
Yeah. The only way you could see is not that is when you look at this formula across here like this.
Yeah.
When you look at this, and you could think about, okay, what's P1? Then you say, okay, what's P2? P2 is when you take off, when you only look at the first two terms. Then you look at P3, then you'll be able to see the general thing. But seeing the general thing doesn't mean that n is some big number or anything like that. The restriction here is that n must be less than C, and in the other one, n must be greater than or equal to C. Right? Okay, so this is Pn for this case, and for n greater than or equal to C, our Pn, if we have until, we could finish before if you want. Yeah.
No, like something that I mean, so no, when the kids
Okay. All right. Okay. Yeah, no problem.
because we also like they are asking for one and see for that. I absolutely as well.
So the other thing was this, that going to take 2 hours and 45 minutes, all right?
Okay.
Very classic.
Yeah. So, okay. All right. You need a break or something?
Bueno, tengo una regla casi de esa vida, pegando y tocando. No, man.
Maybe you try to ask me about it.
Right. Oh, okay.
And that's what I wasn't getting on. I kind of set my mind. What do you want to discuss?
Okay, let's go the whole distance, right? So we nearly, so we nearly off the block, right? So we already off the block already, so we could go the whole distance. So this one here. So Pn now when n is greater than or equal to C is this, but we found P0 already. So all we do is we substitute those values inside. All right, so I'm not going to go through the expectation of LS and LQ and things like that. So I'm going to drop that example. Right. Right. So okay. Okay, so we'll stop here with the queuing and things like that, right?
Right, I will just something that this is
Right. Yeah. So okay. So as an exercise, you find LS, right? LQ, LS, WQ, WS. All right. So, okay. So I'm going to stop, right? I'm going to end the class now. So I want those of you online to stay online. And